Hello elements, welcome to Unit E review. Unit E is a really big unit. It has Chapter 14, Kinetics, Chapter 15, Equilibrium, Chapter 16, Acid bases including weak acid bases. Chapter 17 is Aqueous Equilibrium including KSP, Titration, and pH of salt solutions. So what I'm going to do is to keep Unit E manageable. I have already podcasted on kinetics as a review, comprehensive review. So I have broken down Unit E in two parts. Unit E comprehensive, where I will go over equilibrium, acid bases, salt solution, KSP. But I'm not going to podcast again on kinetics. I am going to attach kinetics review podcast to Unit E kinetics. So you will see two reviews under Unit E and Unit E kinetics. Unit E kinetics is just for kinetics, and then Unit E is for chapters 15, 16, and 17. Now for Unit E podcast. Let's start Unit E with chemical equilibrium, and then I'll get to acids and bases. Chemical equilibrium, and equilibrium means a reversible situation where the rate of forward reaction has become equal to rate of reverse reaction. So basically, what is chemical equilibrium? When rate of forward reaction becomes equal to rate of reverse reaction. And you can manipulate the equilibrium by using Le-Chat's principle. Remember, Le-Chat's principle says a system at equilibrium tends to maintain its equilibrium. So if you apply a stress factor, the system tends to undo it. And what kind of stresses can you apply to a system at equilibrium? You can change its concentration. It'll tend to undo the effect. You can change the temperature. Remember, temperature changes are the only ones that will change the value of equilibrium constant, or K. You can even do pressure changes and volume changes. Pressure and volume are kind of tied together, except you can change the pressure without changing the volume by adding inert gas. And when you do that, really there is no effect, because inert gas does not change the concentration of individual gases or partial pressure of individual gases. Now coming back to the other side of the chemical equilibrium, so these are reversible reaction. How do we quantify chemical equilibrium? We can quantify chemical equilibrium by using something called as law of mass action. And law of mass action says that equilibrium constant, or K, EQ, this is uppercase K, is equal to molarity of products to the moles over molarity of reactants to the moles. This is law of mass action. And how we express it is we have two ways. We can express equilibrium constant as Kc or Kp. Kc is for molarity or concentration. Kp is for partial pressure. Kc applies only to aqueous solutions, never for solid or pure liquids. Kp applies generally for when the pressure is in, when the system, most of the components of the system are gases, and when we are not dealing with pure solids or pure liquids. Okay, so that's Kc and Kp. Now, Kc and Kp are both measured the same way, which is the product to reactant ratio raised to the coefficient, except there's another term which is called Q. So either a system is at equilibrium. In that case, the ratio of product to reactants indicates Kc or Kp. if a system hasn't achieved equilibrium yet or is past equilibrium, then we give the ratio of product to reactant with a quantity called reaction quotient. And the comparison between Q and Kc is, if Q is greater than K, then reverse reaction favored. If Q is less than K, then forward reaction favored, and if Q is equal to K, then the system is at equilibrium. Now, how do you convert Kc to Kp? The equation is Kp is equal to Kc times RT delta N, where delta N is change in number of moles of gases of products minus reactant. So you only consider moles of gases to convert into each other. Now let's look at the third part of equilibrium, is what are the consequences at equilibrium. So if, first of all, rate of forward reaction becomes equal to rate of reverse reaction, does it mean that their concentration of reactant is equal to concentration of product? Maybe, but generally not. Okay, so this is not true. Maybe a special case could be that their concentration turn out to be equal, but generally they're not equal. And then the last thing that you must remember, any stoichiometric calculation that you do at equilibrium, like calculating Kc and Kp, they must use equilibrium concentrations. So if you're given initial concentration, before you can calculate Kc or Kp, you must change initial to equilibrium concentration. And to do that, generally you use a ice chart. And the big concept here to remember is that solid and liquids are not included. So that is equilibrium. Now moving on to acids and bases. You know the naming of acids. Please go over chapter 7 and look at naming of acids and bases. What I'm going to talk about is acids and bases. First of all, let me talk about the nature of acids and bases. So there are two types of definitions. One type are practical definitions that are in use in day-to-day life. The other type of definitions are conceptual definitions, and I'm going to go over both of these. The practical definition of acids are that they are sour, they turn litmus, they turn blue, litmus red, okay, and the base definition is that they are bitter, they turn red, litmus blue. Litmus is a special type of paper. So these are the general definitions. Now the conceptual definition for acids and bases are three. Arrhenius definition, where acid is, it can only be in aqueous solution, and acid is something that increases H plus and base increases OH minus. The second definition is Bronsted and Lowry. It doesn't have to be aqueous, and acid is proton donor and base is proton acceptor. And the third definition is Lewis acid and base, which is the broadest definition, In Lewis acid and base, remember LAEPA, Lewis acid electron pair acceptor, and Lewis base is electron pair donor. Okay, so from here let's talk about the second big section, which is how does equilibrium apply to acids and bases as equilibrium reactions. So there are conjugate acid base pairs, and these conjugate acid base pairs differ from each other in a proton. So H plus and HCl, right, differ from each other in a H plus or H plus. So acetic acid and acetate. Similarly, HCl and Cl minus. These are conjugate acid base pair because they differ from each other in a proton. And at equilibrium, there are dissociation constants. What all dissociation constants have we studied with regards to acids and bases? Ka and Kb. And Ka times Kb gives you Kw. Ka, let's now look at each one of these in detail. Ka, then let's look at Kb, and then let's look at Kw. So Ka generally is for acid, for weak acids, and it shows weak acid strength. The larger the Ka value, the stronger the weak acid is. Similarly, Kb shows the weak base strength, and the reaction for weak acid is Ha plus H2O, equilibrium sign, H3O plus A minus, and the Ka is molarity of H3O plus times A minus over HA. We do not include water because it's pure liquid. And remember 5% rule. If the percent dissociation is less than 5%, you don't have to do quadratic. You can ignore the minus x from denominator and then go back and check if percent dissociation is well within 5%, then you can easily ignore it. Similarly, Kb shows the strength of weak base, and the equation that goes with weak base is B plus H2O gives you BH plus OH minus, and the Kb is BH plus's molarity times OH minus's molarity over B's molarity. Again, 5% rule applies to it. Remember, when you calculate X in case of Kb, it gives you molarity of OH ions. If you're asked pH, then you got to subtract from 14 to get the pH. Kw has the value of 1 times 10 power negative 14, is called the ion product of water. And from here we can talk about the next part of acid and bases, which is pH, and I'm going to continue on here on the next page. Okay, so we had acids, bases. Continuing on from the previous page, you can draw the same one. Then we talk about the pH of acids and bases. The pH is defined as negative log of molarity of H3O plus or H plus, hydronium ion. And there is a pH scale which goes from 0 through 14. 7 is neutral, 0 through 7 is below 7 is acidic, above 7 is basic. And remember the pH box we drew in class to convert between H plus, OH minus, pH and POH. And how do you do pH calculations? You can do pH calculations for strong acid or strong base. It's easy. because in strong acid and strong base there's complete dissociation, so you can assume if you have 1 molarity of acid, it will make 1 molarity of H plus as well, and you just do negative log of that. Similarly, in case of base, you can make the same assumption. However, if you have a weak acid or a weak base, you cannot make the assumption that 1 molarity of a weak acid will give you 1 molarity of H plus. That is why you need to use an ice chart to figure out the molarity of H plus at equilibrium, and then you do negative log of X, and that gives you pH for weak acids, and negative log of X will give you pOH for weak bases. Similarly, in weak species, you also have salts, salt hydrolysis, and you know that weak acids will make acidic solution, weak bases will make a basic solution. But how about salts? Salts hydrolyze if it is an anion. So first of all, in salt hydrolysis, only ions from weak acid or weak base will hydrolyze. So if you have a salt like ammonium chloride, because chloride comes from HCl, it will not hydrolyze, but ammonium comes from ammonia, which is a weak base, it will hydrolyze. Okay, and the hydrolysis reactions go like that. Anion will hydrolyze to give you OH minus. The way I remember is either it makes OH minus or H plus. If it is anion, it makes OH minus, and if OH minus is formed from here, HA remains, and then you write a KB expression, which is HA times OH minus over A minus. If you are hydrolyzing a cation, then it will make BH plus is your cation. It will make B plus H3O plus, and in that case it makes the solution acidic, and you write it as B H3O plus over BH plus. Okay, so these are your acid and these are your cation and anion hydrolysis. And then going back here, what if, guys, would the pH be same for a 1 molar acetic acid and 0.1 molar acetic acid? Answer is no, because molarity of H plus ions will be different. Just wanted to clarify that one point. Now the third thing we need to consider with regards to calculation is how do we do calculation for polyprotic acids. Polyprotic acids are acids that have more than one proton that can be donated. Remember, these donations happen stepwise. So if it is a polyprotic acid H3A, it will break into H2A minus plus H plus, and then H2A minus will break into HA2 minus plus H plus, and HA2 minus will break into HA3 minus plus H plus, and corresponding you can write Ka1 expression, Ka2 and Ka3. Remember, for any polyprotic acid, Ka1 will always be greater than Ka2, which will be greater than Ka3. So if you're trying to figure out a pH of polyprotic acid, it is determined by first step only. If you're asked to calculate H plus concentration, you'll have to do all 3 steps or 2 steps, but if you're asked to determine pH, it's determined by the first step only. The second thing I want to remind you here, because we're talking about strong and weak acids and bases, if you have a mixture of a strong acid and a weak acid, since weak acid's dissociation is so small and it will be further subdued due to common ion effect, the pH will be determined by the pH of strong acid. And then the last part here that I wanted to address is the titrations with acids and bases and then buffers. So I'm going to go to next page to deal with titrations, or rather let me do buffers first and then let me come back to titrations. So on the next page I'm going to do buffers. So we had our acids and bases, and now we're going to talk about buffers. So buffers are solutions that resist change in pH. Buffers are weak acid plus its conjugate base. Such kind of buffers are called acidic buffers because their pH lies in acidic region. And the second type of buffers are weak base plus their conjugate acid, and these buffers are called as basic buffers because their pH lies in basic region. So the general formula for acidic buffer is HA minus, while this is BH plus. The most common acidic buffer is acetic acid acetate buffer, and the most common basic buffer is ammonia ammonium buffer. How do you calculate the pH of buffers? To calculate the pH of buffer, if it is simple buffer and no acid or base has been added, you can simply use HH equation, Henderson-Hasselbalch equation, or you can use ice chart. But if buffer has been neutralized somewhat by acid or base, or some acid or base has been added to it, then you first have to do neutralization chart or ICF chart, and then you have to either use Henderson-Hasselbalch or ice chart. Remember, the only place you cannot use Henderson-Hasselbalch in the second step is at equivalence point. You have to use ice chart for that because you have no more acid or base left at equivalence. The pH is determined by the salt. Now, neutralization are easier reactions to write because you'll have a buffer either HA or A minus, and you have BH plus. So if you're adding base, then the acidic component of both will come to rescue, and if you're adding acid, then the basic component will come to rescue. So you can write neutralization. Ice equations can either be acid dissociation like HA setting the equilibrium to H plus A minus, or the base equilibrium like B plus H2O forming BH plus plus OH minus, or if it is at equivalence, then it could be cation or anion hydrolysis equation. So you have to choose one of those four equations in second step here. That's how you calculate the pH of buffers. And the last part in this very long unit is acids and bases and titrations. Titrations are a methodology to figure out the molarity of an unknown acid or base. Standard solution is a solution whose molarity is known accurately. Endpoint is where indicator changes color. Equivalence point is where moles of acid becomes equal to moles of base. Indicator is a weak acid or base that changes color around the endpoint. Because indicators are weak acid and bases themselves, you do not want to add too much of them. Now, titration curves are monitoring the pH changes in pH with the volume of titrant added. And we have three different titration curves that we'll study today: strong acid, strong base; weak acid, strong base; weak base, strong acid; and then polyprotic acid you can draw on your own. Strong acid, strong base generally start very low, pH close to 0, because it's a strong acid initially, and then pH changes sharply around endpoint, and endpoint is at pH 7. And after the endpoint, the pH is fairly high too, because it's a strong base that's determining the pH. Now for weak acid, strong base, there are some differences. First thing, you do not start very low. Initial pH is somewhat higher. Second, pH changes gently around the endpoint, and the middle of this S-curve is the endpoint, and endpoint is in the acidic range for a weak acid, strong base titration. Also, you see a gentle change in the pH around the endpoint, not a sharp change, because a buffer is formed. When you add a strong base to a weak acid, it forms a buffer which resists change in pH, hence a gentle change in the pH. And that leads to two more keywords. This you know is equivalence point, middle of S. Half volume of titrant added from the equivalence point. This pH is called as half equivalence point. Half equivalence point is very important because at half equivalence point, pH shows the pKa of the acid. That's one thing to remember. Other thing to remember is maximum buffering zone is on both sides of the half equivalence point. Now I'm going to draw weak base and strong acid. So obviously you'll start it in the basic region. Because it's a weak base, it will not be very high up initial pH, and then it gently changes around endpoint in basic region. Why is the endpoint in basic region? Because it's anion hydrolysis that's determining the pH, while in weak acid it was the anion hydrolysis in weak acid and cation hydrolysis in weak base strong acid titration. Again, around half equivalence point there is maximum buffering zone, and that's why pH kind of changes gently, and the ending pH is not it's fairly low because you have a strong acid here. So that is weak base strong acid titration. In a polyprotic acid, you'll have one gentle S-curve indicating each equivalence point. So if it is a triprotic acid, you'll see 3 S-curves in a titration. If it is diprotic, you'll see 2 S-curves. And remember, mole ratios matter. So even though you might have a triprotic acid reacting with a base, but if you take only 0.1 mole of this, 0.1 mole of this, then it will neutralize only first neutralization. You will have H2PO4 minus plus H2O, because even though it can donate all its 3 protons, there is only enough NaOH to remove 1 proton from it. Okay, keep that in mind. And with that, I think major parts of Unit E are covered except for KSP. So I'm going to just quickly go over KSP as well. This sure is a long podcast. KSP shows you the equilibrium of a partly soluble salt like lead bromide between its dissolved ions and its undissolved ions. And this is called KSP, which is the product of its dissolved ion. And this dissolved ion is generally called as molar solubility, which for all practical purposes is equal to the solubility of the ions or dissolved salt. On KSP, you get 3 types of problem. Given molar solubility, calculate KSP, and these are molar solubility. The only thing you got to keep in mind, if it is given in grams per liter, you got to change it in moles per liter. It's molar solubility. The second type of problem is given KSP, you figure out molar solubility, and that's a reverse process. You can do that. If we were to write it as X for molar solubility, then the bromide solubility will be 2x because it makes 2 times as many bromides. Or if you're trying to figure out lead bromide solubility, it will be half that of bromide. And the third type of problems here are, will a precipitate form? And to do this kind of problems, you have to compare Q to KSP. If Q is greater than KSP, then a precipitate forms. Please go over the chapter 17 notes to clarify this further. And that's the end of review podcast for Unit E. Thank you for listening.